Okay, here we are. Free fall practice problems. Number one, what is the meaning of free fall? Explain and give an example of an object in free fall and not in free fall. So, whenever something's in free fall, we're talking about that it's only under the influence of the force of gravity, right? No air resistance. So, really on Earth, you're not going to see things in true free fall, but they'll be nearly in free fall, right? So an example of an object truly in free fall, if you really looked at the Apollo 15 astronaut dropping the feather and the hammer on the moon, that was an example of true free fall when they hit the lunar surface because there was no air resistance there. Or obviously something in a vacuum chamber here on Earth too. An example of an object not in free fall, we dropped the piece of paper and obviously that took a long time to fall to the ground, so that would not be in free fall. Or if something's powered too, like an airplane is not in free fall, assuming the engines are on, as well as there's been sightings, I guess, of individuals in jetpacks at West Coast Airport the other day, and people speculating whether jetpacks would be a real deal, but that would obviously not be in free fall either. Okay. Number two, if a rock in free fall were equipped with an odometer, would the readings for distance fallen each second increase, decrease, or stay the same with time? So remember, an odometer is that thing in your car that registers distance. It tells you the mileage of your car. So if we had a rock in free fall and it had an odometer mounted on it, the readings for distance would increase with time, right? As we'll see down here, by calculating those distances. So let's check our calculations out. We'll get down here. Let's actually see what those distances are. So we can see here in this example that this rock is going to fall this amount of distance in the first second, this much more distance in the second one, this much more, and then this much more. Those distances keep increasing and getting larger as each second goes by. That's what it means to accelerate. So let's do some calculations here. So it says at the 1 second mark, we want to know how far did it fall when it was dropped. So here we have our equation. Distance fallen is 1/2 acceleration times time squared. And if we use 1/2 the acceleration, I'm going to call it -10 instead of 9.8. I'm just going to round it. I don't want to use my calculator here. After 1 second, so if I do 1 squared is 1, times 10 is 10, times 1/2 is 5. So it's going to be 5 meters fallen for the first time interval here. Okay. For the next one, how far does it fall total in 2 seconds? So it'd be the distance from there to there. And so if I do that, it's again 1/2 times -10. Gravity is still the same. But now, after 2 seconds, we want to see what that distance is. So 2 squared is 4, times 10 is 40, times 1/2. That's going to be 20 meters fallen. Total distance. Okay. For the third second down here, so again, that'd be from the total distance fallen. Sorry, I'm doing it freehand there. Oh, not that far, boss. So again, from where it was dropped to the third second, so it'd be that distance. And if we do that here, it'd be 1/2. Acceleration is still 10. I call it -10, rounding it. After the third second, so 3 squared is 9, times 10 is 90, times 1/2 is 45 meters. And the last one would be how far it's fallen total in 4 seconds from the top there. So if I roll through here, again, -10 meters per second squared, but now 4 seconds squared. So 4 squared is 16, times 10 is 160, times 1/2 is 80 meters. Right? Yeah, we did that right. Okay. So I also realized these should really be negative because we're falling below where we started, as long as we know that. But yeah, taking a look here, this distance is 5 meters. This red distance here is 20. The green distance is 45 meters. and the yellow distance is a grand total of 80 meters that it falls from the top here where he drops it all the way down to the ground. Okay. One thing we can notice too is if we make a quick comparison, remember Galileo said the distance corresponds to the square of the time. Well, in one time interval we fell 5 meters. In the next one we fell a total of 20. So after 2 seconds, the second time interval, 2 squared is 4, and yeah, you're right. 20 is 4 times what 5 is. If we look here at 45 meters in the third interval, well, 45 is third interval, so 3 squared is 9. 45 is 9 times the 5 meter mark. And if we go down here, compare the last one to 80, 4 squared, so that's 16, and 80 is 6 times that of the 5 meters. So our proportionality of distance being proportional to time squared definitely works out here. All right, onward to velocity stuff. So we're going to get that falling rock equipped with a speedometer. So here's our rock, and we got a speedometer on it. That's the thing in your car that measures speed. So how do the readings for velocity change after each second? Do they increase, decrease, or stay the same? And here, they're actually going to stay the same amount. It's going to change by the same amount every second, because we know gravity is going to change your velocity by negative 9.8 meters per second each second as it accelerates the rock downward. So let's do those calculations and see what the velocity of the rock is going to be after each second. So at 1 second, rock is right here. So acceleration is change in velocity over time. So let's put in what we know. So we know the acceleration is, I'm going to use 10 again, or negative 10 meters per second squared. I'm rounding the 9.8. So after 1 second, 1 times 10, well, that means my velocity will be negative 10 meters per second. And the negative sign just means it's going downwards. So there's my velocity at the 1 second mark. All right, after 2 seconds, hey, acceleration is still 10. Gravity's still working the same way, but 2 seconds later, 2 times 10 is 20. So now my velocity is 20 meters per second. So maybe I'll draw that arrow twice the length, since it's 20 meters per second now. All right. At the third second, right here, so again, acceleration is still negative 10. I'm rounding 9.8. 3 seconds later, so 3 times 10, that's negative 30 meters per second. So we see our rock is speeding up. I'll try to draw it accordingly. So negative 30 meters per second. And if I go and do 4 seconds, sorry about that. If I do, acceleration again is negative 10. 4 seconds, so 4 times 10 is going to be negative 40 meters per second. I don't have room to draw all that here, so you have to trust me that that is negative 40 meters per second after the 4th second. And maybe that's hitting the ground, right? So it would impact the ground going 40 meters per second. And again, if we look, we see the velocity is always changing by 10, right? Negative 10 to 20 is a change of 10 meters per second. 20 to 30 is another change of 10 meters per second. Okay? 30 to 40, again, gravity is always changing our velocity by about 10 meters per second every second when it's in free fall. Thanks, everybody.